Hi everyone, welcome to my second video on potential outcome. In this video, I'm going to talk about the potential outcome and causal DAG. You see, in the last video, I told you everything you need to know about potential outcome. And last video or part. Then I had a three-part video on do calculus and causal DAG. DAG, do calculus, and front backdoor criterion. Three-part video. And now I want to talk to you about the the idea of potential outcome and DAG, the relationship between them, and also identifiability condition, relationship between them. All right, so this video is this video because we want to have a reason to know both of them, right? In the literature, economists usually know PO, potential outcome, and computer scientists, they know DAG. During my graduate study, I learned both of them. In the PhD, I started with DAG. My background was in probabilistic graphical modeling, but then eventually I learned a potential outcome, and then epidemiologist approach is a combination of both. I may talk a video about the G estimation, G formula, if you're interested. But now let's talk about this. All right. We talk about potential outcome that, some recap, Y subscript 1 means that potential outcome when treated means that treatment is T is equal to 1 for people that get treated. And Y subscript 0 potential outcome when not receive treatment, So T equal to 0. All right. And then we talk about the do calculus and causal DAG in a sense that in a language of do T equal to 1 means that you go ahead and remove the edges that go into the treatment or intervention variable. Remove the edge that's going from any variable to this variable. So we talk about this. It's called intervention on a DAG. All right. So now, today we want to connect them together. It turns out that potential outcome Y subscript 1 when you receive a treatment is nothing but Y given do T equal to 1. That's it. And Y subscript 0 is nothing but Y do T equal to 0. So potential outcome is PO is just equal to intervention on a DAG. That's it. So it says that not only these two frameworks are not different, but also they are actually very, very similar to each other. And one concept from one framework is really mapped to a concept to another framework. In fact, Judea Pearl said that. Pearl said any conclusion in one framework is valid automatically in the other one. Is valid automatically in the other one. All right, great. So now that we understand this one, so remember that if you have a causal DAG, so it gives you two ways to look at that. This is Z confounder, this is a Y, this is X treatment, right? So the Y do X equal to 1, for example, is nothing but, we call this one G, Then we have a post-intervention DAG. We talk about all this stuff in my video, on the three-part video on the do calculus, DAG, and the backdoor front-door criteria. Please go ahead and watch them. It's nothing by removing the edges that go into the variable x. Z, x, y, right. So this one is exactly equivalent to potential outcome if the treatment is set to 1. As simple as that. So in a sense, you can write this one like this. X equal to 1, which is actually very, very, very important connection between them. All right. Now that we understand this, and it's very important that we understand this one thing we need to talk about is the identifiability condition, which is very important in causal inference. I try to talk to them in terms of both framework. So identifiability condition. I talk about that in the language of causal graph. If you remember, I said that graph is not identifiable. Meaning what? Meaning that you start from a do operator, you cannot relate it to the based on observed quantities. The final expression still has a do in it. So that's one way to look at that. But now let's talk about the formally some identifiability condition. There are more than these conditions I talk about that, but these are the main ones. Number one, we need to have well specified and defined, well specified and defined variables and parameters. So what does it mean? It means that you need to clearly specify treatment, confounders, outcome, right? And then make sure that you clearly specify all possible confounders and try to account for as many confounders as possible to close potential backdoor path, potential backdoor or non-causal path. All right. So this idea here is that we need to be very clear on what we are trying to answer. So for example, if you have this DAG, this is X, this is Y, right? So make sure that you specify this variable Z as a confounder, this is a treatment, and this is a Y. And ask yourself what you are trying to do. You are trying to find the expected value of this, for example. Let's say you're trying to calculate the average treatment effect. I defined in the last video. ATE is equal to this. Clearly tell us what you're trying to do exactly. And then try to close as many backdoor paths as possible. Try to identify as many confounders as possible. Another example is this. This is X, this is Y, this is Z1, this is Z2, here, this is Z3. So try to identify all these confounders. All right, otherwise you get a biased result because you are not closing the backdoor condition. Valid for both potential outcome and causal lag, because it's for causal inference, and they are both the same, these two. All right, let's go over next one. Very important. Positivity. What does positivity mean? Positivity means no deterministic treatment. No deterministic treatment, or no impossible treatment. Within the level of confounder, within any level of confounders. All right. So what it means is that probability of X is treatment given Z should be strictly greater than Z. That's why we have positivity. So if you consider any level of confounders for anything, we should not have any treatment, meaning that, let's say X is binary. As an example, X is binary, then P of X equal to 1 given Z, it should be greater than 0. P of X equal to 0 given Z should be greater than 0. In a sense, it's that if one of them is 0, the other is 1. So no deterministic confounder, no deterministic treatment, and or no impossible treatment. Why this is important, guys? Let's say that if this was not true. So this is, in a sense, I want to tell you that not to memorize this stuff. Let's say that you want to calculate this one. This is the outcome given X and Z. Let's just use our probability understanding. We say this one is equal to Y given Y XZ. So this one is equal to what? Y. Use a conditional probability and joint probability stuff. You get this X and Z. One more step. Y P of Y XZ. Look at this. All right. So if positivity is not valid, the denominator is equal to 0, and this quantity is not defined. So the positivity should be valid. That's why I actually drive this expression. Great. Let's go next one. Now the last two are quite important. Consistency. The last three, I would say. Consistency. What does it mean? I defined it in the last video. I also defined in the causal DAG notation as well. Consistency. It means that for the people that actually receive the treatment, the potential outcome had they receive a treatment is equal to observed outcome. That's all it means. All right, so let's say that we have a treatment X equal to 1 or X equal to 0. Okay, so expected value of let me use it, Y1, potential outcome if you receive a treatment among the people that actually receive the treatment is equal to observed outcome. Super important, right? So that you can get from the potential outcome to the language of observed outcome. And I wrote the equation for you guys in the last video. I said y minus x. I used t in that time. So y0 plus x y1. That's another way you can remember the consistency as well. So if x is equal to 1, y is equal to y1. And if x is equal to 0, y is equal to y0. So all it says is that, I will write it in plain English, the potential outcome for those who get treated is the same as observed for treated people. Right? It's very easy to intuitively. So before the treatment experiment starts, you have some potential outcome for all different possibilities of treatment. Then you go ahead and run an experiment and you start to give a treatment to people. So potential outcome, had you treat those people, is the same as observed outcome for the people that actually can receive the treatment. That's what's called consistency. And then we have another one called conditional exchangeability. Conditional exchangeability. Sometimes called ignorability as well. Super important. Maybe the most important one. Conditional exchangeability says what? It says that potential outcome y0 and y1, let's say under the binary treatment, is independent of treatment. This is true for RCT when there is no confounder. There is no confounder. So it says that treatment is independent of potential outcome under no confounder. And this makes sense, right? Remember, not observed outcome. Treatment, of course, is dependent on observed outcome. Otherwise, why we are doing the treatment? But it said potential outcome. The chance that you assign a treatment has nothing to do with the potential outcome that you have. You don't have any bias, in a sense. Now, in case there is a confounder, let's say Z, then Y0, Y1, condition on Z would be independent on X. And makes sense, right? Let's say case of a medical medicine. You want to see whether you should give a treatment, you're considering the potential outcome for certain individuals and see whether, for example, based on that, which treatment you should give to people. Age is definitely a factor here. Age. The people that are older perhaps exhibit different behavior to the treatment, right? So you need to go ahead and control for the age. Once you control for age, means that you say that certain group of people, for the people aged from 45 to 60, okay, for now that all these people from 45 to 60, then the treatment that I am gonna give, the potential outcome is independent of the treatment, the potential outcome. Whether I'm gonna get outcome under treatment equal to 0 or treatment equal to 1 is independent of the treatment I'm gonna assign. The potential outcome means the chance that they get the treatment is equal chance. It's like RCT randomization, pure randomization. So this might be hard for you to see that. This is where DAG is gonna come to the rescue. So assume that we have a DAG like this. This is a Z, this is a X, and this is a Y. So this conditional exchangeability, what it means here is that if you condition on Z, you block all the backdoor path, all the non-causal path, right? Because in the RCT, this is like the RCT, randomized control trial or A/B testing, there is no confounder. And that's why we have exchangeability. But here there is a confounder. So this set of Z or set of variable that close all the non-causal path, backdoor path. You see how potential outcome and causal DAG are related? So this C or set of variables that block all non-causal backdoor path. All right, great. So remember, what's the conditional exchangeability? It's saying that potential outcome is independent of treatment. So the fact that I assign a treatment has nothing to do with the outcome I expect. It's independent of that. It's like RCT. Some group of you receive the treatment, some group of you do not receive a treatment. And the treatment assigned to is completely random. It's independent of what I expect at the end. All right, so but that's what we mean. And then when you have a confounders, of course, this is gonna create a problem. So you have to condition, control, like fix the age, fix the gender, so whatever. You have to control for that. All right, that's good. That's called conditional exchangeability. And then we have something called sutva. All right, so now this sutva is actually pretty interesting. What does it mean? It means about the no interference. So a stable unit treatment is an acronym for something. I will mention it later. But then SUTWA, what's the important thing to learn about SUTWA? It's not that what's the acronym. It's that what exactly does it mean? SUTWA means that potential outcome for a unit is independent of how other individuals or units are treated, or others or individuals are treated. So no interference between the individuals. Interference, right? So potential outcome for a unit, for an individual, is independent of how other individuals or units are treated or they receive the treatment. Okay, so this is majority of time actually is false in the literature. Why? Let's consider a case of vaccine. We want to see that potential outcome is whether the person is getting vaccinated or not. Let's say you're in a family. If majority of people in a family are vaccinated, then you have an intention or motivation to get vaccinated as well. So in a sense, you get a their decision to go and get vaccinated will influence your mind as well. So there is an interference as well. All right, so now SUTVA, the reason why they mention it is because it's a long acronym and it doesn't really help you much to understand what it means. SUTVA stands for a stable unit treatment value assumption. The best way to realize it is a no interference between the units or no interference between individuals, right? Which majority of them actually fail in the literature. All right, so these are the important identifiability condition in the causal inference. We look at them in terms of this is a majority, it's very easy to look at in the potential outcome. So some of these are easier to look at in potential outcomes, some of them are easier to look at in causal DAG. And that's why you need to know both of them actually fairly well. So SUTVA is easier to look at in terms of potential outcome. Conditional exchangeability is very easy to see in terms of DAG. It's actually very, very attractive in terms of causal lag. Consistency, I would say that it's easy to look at that in both sense. Then positivity as well. It's very easy to see it in terms of potential outcome or in terms of the actually language of mathematics, language of the probability. And the first one is also better or easier to look at that in terms of causal DAG. Hopefully I give you enough motivation on why we need to learn both of them and how we can relate one to the other. Like always, if you like this video, please like, share, and subscribe to the channel. If you have any question, please let me know, and I do my best to respond to your question. Thank you, and see you all in the next video.